So here let us go to the next part of the discussion, that is catalysis. If we go to the concept of catalysis, this concept of catalysis was actually introduced by, that is, Berzelius. Concept of catalysis was given by Berzelius. So if you go to the catalyst, catalyst is a substance which accelerates or enhances the reaction rate without undergoing any chemical change in its mass and composition, mass and structure. This is catalyst, and the process we call it as, the process is catalysis. The process we call it as catalysis. So here when you go for the catalysis, here actually depending upon the, based on type of phases of the catalyst and reactant molecules. Based on the catalyst and the reactant molecules, this catalysis is divided into two types. That is, one is you can take divided into two types. One is, that is, homogeneous catalysis, and the other one is, that is, heterogeneous catalysis. So here what is happening here is, basically if you broadly classify the catalysis into different classification, you can give different classifications. Actually, the broader classification of catalysts, they are of many types. That is, one is we can take positive catalyst, negative catalyst, negative catalyst, and you can just add that is promoters, poisons, then auto or self catalysts. So that means, apart from the homogeneous catalysis and the heterogeneous catalysis, if you take, the catalysts are divided into, based on the other action, the catalysts are divided into the remaining rest of the catalysts. You can say that is positive catalyst, negative catalyst, promoters, poisons, auto catalysts, and catalysis. What are the characteristics of catalysts actually? If we go to the characteristics of catalysts, a catalyst is a substance which never gets consumed in a reaction. Small amount of catalyst, small amount is enough to change entire rate of reaction. Then catalyst is always specific. In nature. The formation of product depends upon what kind of catalyst you are using, and also the action of catalyst also depends on nature of nature of reactant molecules. One of the most important point what we have to remember here is whenever the catalyst is added, the catalyst actually describes the different path. Actually, action of catalyst on the reaction rate, action of catalyst on the reaction rates is always it lowers. The action of catalyst on the reaction rate is done by lowering of activation energy and describing a new path. And it describes a new path. Sometimes, suppose if I am plotting a graph taking the potential energy on of the reacting molecules on the y-axis and progress of the reaction on the x-axis, if we take, then you find that here, that is, without adding catalyst, you find a peak like this with a greater energy in the molecules. But once you add the catalyst, you find that the height of the curve gets flattened, and you find that here it makes more number of molecules to involve in the chemical reaction. So you can see the difference here. So this is with the addition of catalyst. So here we think that this is EA and this is EA dash. This is EA dash. So you find that EA dash is less than EA because here you are adding catalyst. This curve represents addition of catalyst. This is no catalyst. So you can see from the graph that by adding catalyst you can make out the difference. The addition of catalyst in a given chemical reaction always describes a new path, and it lowers the activation energy. Because of the lowering of activation energy in the molecules, you find that more and more number of molecules undergoes effective collisions, and you find that more number of molecules comes into the formation of products. So this is how the catalyst will influence, and this is a broader prospective classification of catalysts. And now we are going to have a detailed discussion of the homogeneous catalysis and the heterogeneous catalysis. So here if you go to the next part of the discussion, that is based on the phases of the physical states of, so again once again I repeat, based on the physical states of reactant molecules and catalyst. Here the catalysis is divided into two types. The first one is, let me say, homogeneous catalysis. So in this homogeneous catalysis, because we are saying that the reactant molecules and the catalyst is in the same physical state or in the same phase. Suppose one or two examples let us take. For example, if I am taking one of the best example in the homogeneous catalysis is, that is, you can take SO2 gas plus O2 gas reversible reaction. The catalyst is nitric oxide gas, and you find that SO3 gas is produced. So I repeat, if you take this particular reaction, the reversible reaction in the formation of sulfur dioxide through the contact process, in the formation of in the manufacture of sulfuric acid, in the formation of sulfuric acid through contact process, this is the preliminary reaction, wherein which if you balance the equation, take here 2 moles of sulfur dioxide and 2 moles of sulfur trioxide. So 2 moles of sulfur dioxide reacts with 1 mole of oxygen gas to give 2 moles of sulfur trioxide gas. So what we are noticing here is, like, you are finding that here these are the reactants and which are in the same gaseous phase, and here this is the catalyst. Yes, the catalyst is also in the same gaseous phase. So we can say that both the reactants and the catalyst, both of them, they are in the same phase. That's why we can say that this particular reaction is obeying the homogeneous catalysis. So go for one more reaction. One of the best reaction is, like, for example, hydrolysis of ester, CH3 carbon double bond oxygen, O C2H5 plus H2O. This is aqueous, H2O aqueous reversible reaction. You can take small amount of acid, again it is aqueous, you get acetic acid, carbon double bond oxygen of OH of aqueous plus C2H5OH of aqueous. So what we are noticing here is like this is, you are finding that again the ester, this is ethyl acetate, this is ester, ethyl acetate, ethyl acetate ester, upon hydrolysis it gives acetic acid plus ethyl alcohol and small amount of acid is generated. Actually what is happening here is when ester is subjected to hydrolysis, this after hydrolysis you get small amount of acid. This acid is itself is going to act as a self catalyst for this hydrolysis. So suddenly you find that there is a speed up in the rate of the reaction. Suddenly you find more and more amount of acid and alcohol being generated. That is the mechanism of this hydrolysis of ester. So here H plus ion which is obtained from the acetic acid is acting as a self catalyst, and based on that you find that more amount of ester upon hydrolysis it gives the carboxylic acid as well as the ethyl alcohol. So this is one best example of the homogeneous catalysis, because here the reactants are in the liquid phase and the catalyst is also in the liquid phase. And one more example I can give for homogeneous catalysis is, that is hydrolysis of sugar. If you go for hydrolysis of sugar, yes, you can take C12H22 C12H22O11 in the presence of, that is aqueous plus H2O, aqueous reversible reaction, small amount of acid you take, again this is also aqueous, you take this as aqueous, then you can take, this is C6H12O6 plus C6H12O6, so you can take this as glucose, again fructose, glucose and fructose, this is aqueous and this is also aqueous. So that means we are finding that again the reactants and the catalyst are in the same phase. So these three reactions will make us to understand that what kind of mechanism is operating in the case of homogeneous catalysis. Now go for heterogeneous catalysis, plenty of examples you can take, that is heterogeneous. If you go for heterogeneous catalysis, if you are going for heterogeneous catalysis, I can say that plenty of examples you can take for heterogeneous reactions also. For example, N2 gas plus 3H2 gas, reversible reaction, you can take Fe2O3 solid acting as a catalyst, so 2NH3 or 2 moles of ammonia gas. So you are finding that here the reactants and the catalyst are in the different phases. So the reactants are in the gaseous phase, they are in the gaseous phase, and Fe2O3 is a catalyst, it is in the solid phase, so that we can understand. So this is the best example of providing the heterogeneous catalysis. So this is first one. Go for second. Similarly you can even take like decomposition of that is formation of hydrogen iodide. So H2 gas plus I2 gas, reversible reaction in the presence of platinum acting as catalyst, platinum is a solid, so 2 moles of HI gas. You are finding that the reactants are in the gaseous phase and the catalyst is in the solid state. Again likewise you can take many number of examples. Hydrogenation of oils, so if you take oils are liquids, oils are in the liquid state and hydrogen is a gas, and you find that the catalyst nickel, Ran and nickel is in the solid state, so they are getting converted to fats. Fats are solids. So this is a special type of reaction wherein which all the reactants and the catalyst are entirely in the different physical states. So definitely we can apply this for the heterogeneous equilibria. So like that we can take umpteen number of examples. Last but not the least, you can also take KClO4 potassium chloride is a solid. So when you're heating strongly, you add a MnO2 solid. Of course this comes under the homogeneous catalysis, KClO plus KClO solid plus O2 gas. So here you are finding that the catalyst and the reactant are in the same state, so this is an exception again. This is homogeneous. Go for homogeneous. You can take, likewise you can take SO2 gas, 2SO2 gas plus O2 gas. If you take reversible reaction, vanadium pentoxide, solid you can take, and 2 moles of SO3 gas. So successfully we have classified the homogeneous catalysis as well as the heterogeneous catalysis, and we have studied what kind of mechanism is taking place in both the cases, that is homogeneous catalysis and the heterogeneous catalysis. So here, based on the action of catalysts, here based on, let us go for the classification, based on action of catalysts, based on the action of catalysts, here we can take, that is number one, first one, positive catalyst. Positive catalyst. If you go for a positive catalyst, it increases rate of reaction. All the substances which increases the rate of reaction are said to be positive catalysts. Example, if you go for, that is decomposition of hydrogen peroxide liquid in the presence of sunlight. Decomposition of hydrogen peroxide is a photochemical reaction. Hydrogen peroxide easily gets decomposed in the presence of sunlight, so it gives something like H2O liquid plus oxygen gas. So here I can say that here H mu that is sunlight is a positive catalyst. It is a positive catalyst. Now go for the negative catalyst. Go for the negative catalyst. Suppose for example, if you go for negative catalyst, go for a negative catalyst. If you go for a negative catalyst, it decreases the rate of reaction, which decreases the rate of reaction. So example, you can take the same hydrogen peroxide liquid. If you add a small amount of, that is acetanilate, H3PO4, you can add H3PO4 or acetanilate, then you find that the decomposition of hydrogen peroxide, no reaction. That means here the hydrogen peroxide H2O2 decomposition is decelerated by the small amount of phosphoric acid or acetanilate. So these will act as negative catalysts. Sometimes we can go for, that is promoters. What are promoters? Promoters, they actually increase the upward arrow represents the increase. So they increase the activity, the catalyst which increase the activity of the catalyst. They increase the activity of catalyst. Here the increased activity means increase in porosity and increase in surface area and removal of impurities, so that it provides the seat of chemical forces for the reactant molecules to settle on the surface of the catalyst. So the best example for promoters is, like, we can take molybdenum. Molybdenum is a promoter. Molybdenum is a promoter for the iron in the manufacture of ammonia manufacture in Haber's process. Likewise, this is first example. If you want, we can take one more example, that is, so here if you take one more example, that is in the hydrogenation of oils when they are converted to fats, we take nickel as a catalyst. For this nickel, you can take, that is, for nickel the promoter is, that is arsenic oxide, or you can take tellurium dioxide will act as a promoter. And also in the decomposition of that is paraffins, in the decomposition of alkanes, to, that is alkenes plus hydrogen. So you can take for cobalt, for nickel or platinum, for nickel or platinum, aluminum chloride will act as a promoter. So promoters always increases the activity of the catalyst, and it will ensure that the given rate of a reaction it speeds up, and the catalyst will try to absorb more and more number of the reactant molecules, such that the old bonds will break and new bonds are going to form, and effectively, efficiently new products are going to be released into the in the chemical reaction. So this is the function of the promoter. So opposite of promoters is poisons. If you go for poisons, next is, let us go for catalytic poisons. Catalytic poisons, if you take catalytic poisons, which decreases the activity of catalyst, If you're going to the decreasing of activity of catalyst, so in the manufacture of ammonia, N2 gas plus 3H2 gas, reversible reaction. For iron, if you add small amount of carbon monoxide gas, not cobalt, it is carbon monoxide. Carbon monoxide gas is acting as a poison in controlling the yield of ammonia. Similarly, in the Rosenmond's reaction, for Lindlar's catalyst, the palladium will act as a poison for barium sulfate. It acts as a poison for the barium sulfate mixed in quinoline, acting as a solvent. So like this we can take plenty of examples for that is catalytic poisons. So we have promoters, we have catalytic poisons, then we have negative catalysts, and we have positive catalysts. So we have studied 4 different types of catalysts depending on their specific action. So the next part of the catalysis is, that is, if you go for auto or self catalyst, here what is the principle involved in auto or self catalyst? Here no external catalyst is added in the reactant molecules, if one of the product which is obtained in a given chemical reaction, if one of the product which is obtained itself will act as a catalyst, then such reactions we can call them as, that is, the self catalyst or the auto catalyst. So for example, one of the best example in the self catalyst is, that is, standardization of oxalic acid in acidic media. Using KMnO4 solution, potassium permanganate solution. So how do you write the equation for this? So KMnO4 plus H2SO4 plus then oxalic acid H2C2O4. Oxalic acid gives you K2SO4 plus MnSO4 plus carbon dioxide plus water. If you take, so if I am taking 10 moles of carbon dioxide, then I will take here 5 moles of the oxalic acid. If I take, because there are 2 potassiums, take 2 over here, then we have 2 manganese, so therefore take 2 over here. The number of sulfates there are 2 into number of sulfates, total 3 sulfates are there. So I think if I am going to take here 3, then I think the number of sulfates also they are going to get balanced. So 3 sulfates are balanced, then 2 potassiums are balanced, 3 into sulfate, 3 sulfates are balanced, 1 sulfate, 2 sulfate, 3 sulfates are balanced. Then you have total number of hydrogens, 5 to 10, 10 and 6, 16 hydrogens are there. So here we have so I am going to take 8 over here, 8 to the 16 oxygens. So let us not touch the sulfates. Here 3 sulfates are balanced, here also 3 sulfates are balanced, 5 5 4s are 20, 20 plus 8, 28 oxygens are there. So here 10 to 20 plus 8 oxygens, 28 oxygens, and number of hydrogens are also balanced. So what is happening here is, if I write this in the form of ionic equation, from this equation, if I write this in the form of ionic equation, permanganate ion plus sulfate ion plus oxalate ion gives you again sulfate ions plus manganese ions, because here also we get a sulfate, manganese ions plus carbon dioxide plus water. So what we are noticing here is permanganate ion. If you take permanganate ion, here the permanganate ion is plus 7 oxidation state, and here the manganese ion is plus 2 oxidation state, and here you can see that the permanganate ion is getting reduced, and one of the manganese ion, this manganese ion itself will speed up the reaction. It will act as a self catalyst. This will act as self catalyst, and it speeds up the reaction, and it favors more and more amount of the potassium permanganate to react with the oxalic acid to give carbon dioxide and water. And once the manganese ion is formed, you find that there is also a color change which changes to pink color. Once you add an indicator for that, no need of adding indicator, at one particular stage suddenly the pink colored solution becomes colorless, because potassium permanganate is already pink. So by the time manganese ions are going to form, it becomes colorless. That means it is just a self indicator. This reaction is just a best example for that is self indicator. So this is one of the best example for that is autocatalyst or self catalyst. So if you go for second example, that is hydrolysis of ester, if you take again here also ethyl acetate aqueous plus H2O aqueous, here small amount of H plus ion which is actually generated from the acid which is formed here, acetic acid, plus that is ethyl alcohol, C2H5OH liquid. So all the protons whatever are necessary will be generated in the form of H plus ion acting as catalyst. So these H plus ions will enhance or speeds up the given reaction, and more amount of the acid, carboxylic acid and ethyl alcohol is formed. So therefore this is the best example to serve as a self catalyst. So these are the two best examples, and you can also take one more if you want. I'll give you one more. The decomposition of arsenic hydride. Arsenic hydride decomposes to give arsenic plus hydrogen. So 3 moles of gas. This is 2 and this is solid. So here arsenic itself will act as a self catalyst. Third example. So if you go to the next part of the discussion, that is theory of catalysis. Theory of catalysis. In this theory of catalysis, let us go to the first one, that is adsorption theory of catalysis. Adsorption theory of catalysis. In this adsorption theory of catalysis, what we are noticing here is the principle involved here is that is chemisorption, and you find that one is it involves chemisorption, it involves desorption, and finally you find that chemisorption and desorption are the two stages in the adsorption process. What we have to notice, what we need to understand here is, if you go for the, suppose if this is the surface area of the catalyst, then I will say that the catalyst will provide certain active centers. These are seat of active centers. Every catalyst, it has certain specific active centers, because this is a surface area. If I say that this is surface area of catalyst, this is seat of active centers. These are nothing but, these places are called free valence electrons. We can say free valency electrons. So that means it is trying to create a seat of chemical forces. It is allowing. So this is the surface area of the catalyst, and you try to add the adsorbate molecules. Adsorbate molecules means you take H2 gas. So for example, I am taking H2 gas, and you also add a little amount of the ethylene gas also. Suppose I am taking CH2 double bond CH2 gas. These are the reactant molecules or the adsorbate molecules. So you get an intermediate complex. So first it forms an intermediate complex on the surface of the catalyst. So when it is forming the surface of the catalyst, you find that a bond occurs here. Temporary bonds occur like this. So here also you find that these active centers can hold the reactant molecules like this. That is, it forms. So you find that here the whole bonds will break, and something like this. CH2 also, CH2. This happens like this. That means it is forming an activated complex. The catalyst is trying to form an intermediate complex. Intermediate complex. Then what will happen? The old bonds have to break. Here the old bonds will break and the new bonds are going to form. When the new bonds are going to form, you find that here desorption occurs. This is the stage where desorption takes place. When the desorption is taking place, the catalyst is regenerated again. The catalyst is regenerated back. It is again regenerated back. So here I can say catalyst is consumed. Catalyst consumed is equal to catalyst regenerated. Catalyst regenerated. So if you go for regenerated catalyst, then here you find that again when old bonds are broken, the new bonds are going to form. When new bonds are going to form, it appears to look like this. CH2, that is hydrogen single bond CH2, single bond CH2. This is H. So this is simply taken as CH3 single bond CH3, that is ethane gas. A new product is formed. Stable new product is formed. So therefore we can see that in this process what we are able to understand is the catalyst is consumed and catalyst is regenerated. By the time the reaction is getting completed, the catalyst is trying to get regenerated, and definitely here it is this chemisorption. One is chemisorption involvement, another one is desorption, and one more is that is the absorption theory of catalysis is applicable for heterogeneous. It is a heterogeneous catalysis. Because the catalyst is solid and the reactant molecules are gases, and in the final stage the catalyst is regenerated with the formation of the stable product. So here if you go to the next part of the discussion, that is second one, intermediate compound formation theory. Intermediate compound formation theory. So here it is applicable for the homogeneous catalysis. Catalyst forms intermediate complex utilizing lesser energy. Utilizing the lesser energy, and in the final step the catalyst is consumed and catalyst is regenerated. So therefore a stable product is formed. Stable product is formed by catalyst regeneration. A stable product is formed by catalyst regeneration. So for example, if you take one illustration, suppose for example I am giving you A plus B, A gas, B gas, reversible reaction, C is also gas, and the product formed is AB gas. So here C is the catalyst, A and B are the reactants, A and B are the reactants, AB is a product which is formed, and C is the catalyst. So what we are noticing here is something like this. In step 1, the catalyst is going to react with one of the reactants and it forms intermediate complex. So it forms A gas plus C catalyst, which is again a gas. It forms an intermediate complex. AC gas intermediate complex. This is a slow step, RDS, rate determining step. Then again in the step 2, you find that this AC gas, again it reacts with the remaining reactant is B. So it forms AB gas plus C gas is formed, and this is a fast step. So here what you are noticing here is, here catalyst is consumed. Here the catalyst is consumed, and here the catalyst is regenerated. So therefore, if you want to add both the equations, you add both the equations. When you add both the equations, you're finding that here the intermediate complex gets cancelled. So A gas plus B gas, reversible reaction, you find that AB gas is formed with the evolution of heat, plus sufficient amount of heat is also produced because it's an adsorption process. The overall process is adsorption. It involves adsorption process, mind you. The process is adsorption, don't forget that. And in the meantime, if you apply the rate for the slow step, if you want to write the rate of reaction, so the rate of a reaction, rate of a chemical equation is given by rate is equal to rate constant into concentration of A into concentration of C. So therefore the rate of a reaction is depending upon the slowest step. The rate of reaction is depending on the slowest step, that is rate determining step, but it is not depending upon the overall reaction. Overall reaction is going to become the elementary reaction, and which gives the molecularity of a reaction. But the rate of the reaction always depends upon the slowest step, that is the formation of intermediate complex, which is utilizing less energy. So that's why it is rate determining step and the slowest step. So in this way we can understand the intermediate compound formation theory. And for this, if you want to take the example for this is a general mechanism. I can say that this is only the mechanism what you have adopted. This is the mechanism, and for this mechanism the best example what you can take is again here 2 moles of SO2 gas, reversible reaction. Of course you need to add oxygen gas, reversible reaction, nitric oxide gas, 2 moles of SO3 gas. So here nitric oxide is acting as catalyst. At one stage it will react with one of the reactant, it forms the intermediate complex. With the help of that intermediate complex, again it will react with oxygen, and finally it gives the stable product wherein which the catalyst is regenerated. So therefore this is nothing but the intermediate compound formation theory. So here the next part of the discussion is that is colloids. This concept of colloids was actually given by Thomas Graham. According to Thomas Graham, he says that colloid means glue like. The meaning of glue like means just like sticky substance, frankly speaking. This is what we have to understand. So according to the Thomas Graham, the colloid is nothing but a glue like substance. So actually if you go for a colloid, what is a colloid? A colloid is simply nothing but it is a heterogeneous heterogeneous solution which contains both dispersed phase and dispersion medium. Which contains both dispersed phase and dispersion medium particles, where can be separated only through parchment membrane. The reason is, in all the colloids or in the colloidal solutions, the particle sizes are macroscopic. The particle sizes are macroscopic. I can say that the particle sizes in the colloids are always in between true solutions and suspensions. Some of the most important characteristic features, if you go for characteristic features, if you take features of colloids, if you take that is type of colloid depends on nature of dispersed phase particles, interaction between dispersed phase and dispersion medium particles. What is nature of the dispersed phase particles? Interaction between the dispersed phase and dispersion medium particles. And one more thing is their rate of flow. The rate of flow is slow. Next is they are opaque to light. And you can see that these colloids, they show the exclusive property of colloids is they show Tyndall effect. Tyndall effect is nothing but scattering of light particles. And if you go for the particle size, as I said, if you go for particle size, that is the particle size is between, that is 1 millimicron to, that is micron. The particle size is between 1 millimicron means 10 to the power of minus 9 centimeters to 10 to the power of minus 6 centimeter. If you go for true solution, if you are going for the true solution, that is 10 to the power of minus 9 centimeter is the particle size of true solutions, and 10 to the power of minus 6 centimeters is the size of that is suspensions. The best example for suspension is, that is suspensions are nothing but sand in water is a suspension. Then you can take paints are suspensions. True solutions, all crystalloids, they are highly soluble in water. All emulsions, paints are actually emulsions. So if you go for crystalloids, for example, copper sulfate is a crystalloid, sodium chloride is a crystalloid. So sodium chloride, when it is dissolved in water, it forms NaCl of aqueous. Copper sulfate, when it is dissolved in water, it forms copper sulfate aqueous. So their solubility is more, so therefore their particles are going to completely dissolve in water. I can say that if all the true solutions, they are homogeneous. All these true solutions, they are homogeneous in nature. All the true solutions, they are homogeneous in nature. And one thing what we have to understand here is, whenever you speak about a colloid, whenever you say a colloid is simply nothing but a sol. We can shortcut, we can call it a sol, and it contains two components. One is dispersed phase. Dispersed phase is nothing but solute particles, and it contains dispersion medium, that is solvent particles. So based on the affinity taking place between the dispersed phase and dispersion medium, based on the affinity, what kind of affinity is taking place between the dispersed phase and dispersion medium, again colloids can be reclassified. These colloids can be reclassified into two types, that is lyophilic colloids and lyophobic colloids. Based on the affinity between the dispersed phase and dispersion medium, they can be reclassified into lyophilic colloids and lyophobic colloids. You know that lyophilic colloids are those colloids wherein which they have more affinity between the dispersed phase and dispersion medium. If the dispersed phase particles have more affinity towards the dispersion medium solvent, then such colloid is lyophilic. Lyophilic is also called as hydrophilic, and they are solvent loving. And lyophobic, if you take, if there is less affinity of the dispersed phase particles over the dispersion medium, then you find that such colloid is going to become a lyophobic colloid. All lyophobic colloids are also called as that is hydrophobic colloids. So all the hydrophobic colloids or lyophobic colloids are solvent haters, and the lyophilic or the hydrophilic colloids are the solvent lovers in the case of the colloids between the affinity of dispersed phase and dispersion medium. So here look at this table, the type of colloidal systems. If you let us have a detailed analysis of what kind of colloids we come across in our daily lives. For example, if you take, you know very well that every colloid is made up of two components, one dispersed phase and another one is dispersion medium. Based on the dispersed phase and dispersion medium only, we are going to come to the conclusion that what type of colloid it is. We can say that here in the type of colloids, and based on the type of colloid we are coming to the examples. So if you take, if you find that the dispersed phase is solid and dispersion medium is also solid, then such colloid we call it as the solid sol. And if it is solid sol, then the examples are alloys. You know very well that even in solutions also, in one of the type of solutions, solid in solid, if the solute is solid and the solvent is solid, then such solution comes under the alloys. Alloys are the solid solutions, because the solute as well as the solvent, both of them, they are in the solid state. So the mixture of the two metals, when they are heated to high temperature, they change into molten state and they convert into liquid state, and again when they are cooled or when they are subjected to condensation, again these molten metals which are in the liquid state, they change back to the solid state. That's why we can say that alloys are the solid solutions, wherein which the dispersed phase and the dispersion medium, both of them, they are in the solid state. And we can take ruby glass. Yes, glass is a super cool liquid and glass contains silicates. Slow cooling of glass is annealing and fast cooling of glass is quenching. So glass is a super cool liquid. When it is heated, it changes to liquid, and when it is cooled or when it is subjected to condensation, it changes to a solid state. So therefore glass, we can call it as the amorphous solid, which is very soft. Then if you go for if the dispersed phase is solid and the dispersion medium is liquid, then again it is simply called as a sol. And if that is the case, the example is solid and liquid type of colloid, we call it as paints, ink, colloidal gold. Gold in water, because here gold is a solid and gold is acting as a dispersed phase and water is acting as dispersion medium. Gold dissolved in water is a colloidal gold. And paints, yes, paints are also the liquid type of emulsions. And if you take ink is nothing but water dissolved in dyes. The dyes gives different kind of colors. So based on the dyes dissolved in a suitable solvent, liquid solvent, it becomes ink, and ink will impart certain color because of the presence of dyes. Go for dispersed phase and dispersion medium. Dispersed phase is solid and dispersion medium is gas, yes, or aerosols. These are very common, where we come across daily in our daily life. Smoke, dust, soot in air. Soot is nothing but the burnt smoke, the black smoke or the tarry smoke which is coming and diffusing into the atmosphere, which gives the black coloration for the given area, then that is nothing but soot. Then if you go for the liquid in solid type of colloid, liquid in solid is always a gel. If it is gel, yes, it's cheese, butter and jellies we can take. Then if you go for liquid in liquid, yes, it is emulsion. Milk is an emulsion. In fact, milk, you know very well that the dissolved the dissolved fats in water is milk. If you go for milk, milk is nothing but milk. If you take the dissolved fats in water is milk. And here cream. Then again, if you go for liquid in gas type, this is one more type of aerosol where we find it in the form of fog, mist, cloud and sprays. And finally gas in liquid type of colloid, if you take, it's a foam where we take froth. Froth is nothing but it is generally a metallurgical term which we use in the extraction of iron from the pyrite mineral ores. We get a froth by adding the eucalyptus or the pine to the given crushed mineral ore. When you add little amount of the frothing agent, then it gives a lot of foam wherein which all the impurities are settled at the bottom, and the pure the pure foam in the form of froth, it comes out, and then it is sent for further purification. So that is a term which is used in the metallurgical operation. Soda water, and finally it is shaving cream. So these are the different type of colloids based on the components of the colloid in the form of dispersed phase and dispersion medium, and whether they have solids, liquids or gases. Based on that, we are trying to classify all these colloids, and these are the suitable examples. So here the next part of the discussion, that is, we know very well that is based on affinity between dispersed phase and dispersion medium. We have A, that is lyophilic colloids, and the other one is lyophobic colloids. So here in the lyophilic colloids, you find that they are solvent lovers, greater affinity between dispersed phase and dispersion medium. These are solvent haters. I can say that lesser affinity between dispersed phase and dispersion medium. This we already know. So now what is happening here is like here when you go for, and one more thing, based on one more classification I would like to give, based on type of solvent, that is dispersion medium. Again they are classified into, suppose if water is the dispersion medium, this is called aquosol. If benzene is the dispersion medium, then we can call it as benzosol. If benzene is the dispersion medium, it is benzosol. Then alcohol is the dispersion medium, then we can call it as alcohol and so on. So this is one type of classification. But in the meantime, if you go for the lyophilic colloids, but if you are going for lyophilic, the most important colloid in lyophilic colloid is lyophilic colloids is, that is associated colloids. Associated colloids. Actually, what I mean to say is that some solutions at a low concentration, they behave as electrolytes. They behave as strong electrolytes. Solutions at low concentration, they behave as very strong electrolytes. That means they become ionic solutions. But suppose if the same solutions But suppose if the same solutions are at high concentrations, if they are at high concentrations, then we can say that definitely they can behave as associated colloids. So what do you mean by an associated colloid? If you go for an associated colloid, these are the colloids which have both hydrophobic and hydrophilic colloids which have both hydrophobic and hydrophilic ends. The colloids which have hydrophobic and hydrophilic ends at the minimum concentration called CMC. This is called critical micelle concentration. CMC is called critical micelle concentration. So critical micelle concentration actually operates at Kraft's temperature. It operates at Kraft's temperature. Critical micelle concentration operates at Kraft's temperature.